Our world is becoming more connected. Billions of people across the globe share information, communicate, and collaborate on different projects. Those projects can range from research writing to software development. Meet Sandra and Andrew. They are using one of those centralized collaboration platforms that allow them to share and update files together. Sandra and Andrew started working together on a new project, and they are sharing their updates. Then, the platform service went down. Sadly, Sandra and Andrew can no longer work together on those projects. Now Sandra, Andrew, and Adam are collaborating together on a project. Then malicious Adam decides to manipulate with their work, so he manually changes their submitted work and resubmits it under his name. A central collaboration platform can allow this to happen, which damages accountability. Now imagine a system that prohibits Adam from doing such an attack and allows Sandra and Andrew to collaborate together safely without interference and with no fear of server failure. Git of Truth is building this technology. It allows collaborators to share their updates together without the need for a central collaboration platform while providing a tamper-resistant working environment.
Good morning, ladies and gentlemen, and welcome to our final thesis presentation. We have been working on this project for a year now, and today we are proudly introducing to you Git of Truth, a trustable peer-to-peer Git-based version control system over blockchain, supervised by Dr. Sherif El-Kassas and Dr. Karim Sobh. Now allow me to introduce to you the team behind all of this. Hassan Kandil, Elia, Merola Tadros, Muhammad, Faisal, and myself, Aliaa Amin. This is our agenda for today. Starting with an overview, in the beginning, let me explain what version control systems are. Well, they are a category of software tools that help a software team manage changes to source code over time. Version control software keeps track of every modification to the code in a special kind of database. It helps teams solve problems, including tracking every individual change by each contributor and helping prevent concurrent work from conflicting. Now, built on top of version control systems, there are collaboration platforms that host users' repositories and enable them to work collectively on these repos and share their updates together. Now, after examining current version control systems, which depend on a central collaboration platform, we found that they suffer from some problems as demonstrated in the video. These problems brief to single point of failure, single point of control and ownership, authenticity and data integrity, synchronization and communication delays, and finally scalability issues. So those problems inspired us to move towards peer-to-peer version control systems and bridge the gap in the current systems, which are the need for verifiable repos and their updates history, and the lack of reliability, accountability, and trust. Here comes our solution to the previously mentioned problems. A peer-to-peer Git-based version control system on blockchain, which allows for developers to collaborate together on different projects in a trustable equal ownership environment without the need for a central collaboration platform to share their updates, while maintaining at the same time the authenticity and reliability of the shared repos and its update history. Now, there are multiple use cases for our system. One example is source code development for companies, in which project managers need to track and verify version changes. It also improves accountability and performance monitoring. Also in university assignment submissions, which prevents students from tampering with submission history even if the repo is stored locally. It also reduces the cost and effort of managing a submission central server. Another example is electronic medical records version control, which allow doctors to efficiently study patients' medical history through tracking records changes. Now, to fulfill this, our general system requirements summed to the following: tamper-proof repositories, storage decentralization, access control, authentication, confidentiality and passive storage nodes, replication and availability, and finally scalability. Our system has three main subsystems. At the bottom of the diagram, you can see the decentralized storage system, which manages the decentralization of the stored repos. It is implemented through IPFS. At the top of the diagram, you can find the blockchain subsystem, which mainly provides the tamper-proof aspect of our project, and it is implemented using Hyperledger Fabric. Finally, the Git client, which mainly connects all of those system components and also connects between all the system and the local Git as well. Now, through our presentation, we will dive into each subsystem, and I will leave the floor now to Marie to explain the decentralized storage subsystem.
Let me begin by explaining the first subsystem, which is decentralized storage. Here, three of our major system requirements are fulfilled, which are storage decentralization, confidentiality, and finally replication and availability. The first fulfilled requirement is storage decentralization. A file system simply is the process that manages how and where data is stored and managed. Let me start with some general info on our chosen protocol, IPFS. It's a peer-to-peer protocol for storing and sharing data in a distributed file system. It consists of several innovations that have been combined together to produce a file system like no other. First of all, content addressing. Instead of referring to objects like pictures and videos by which server they're stored on, IPFS refers to everything by the hash on the file. The idea is that if in the browser you want to access a particular page, then the IPFS will ask the whole network, does anyone have the file that corresponds to this hash? And a node on IPFS that does can return the file. Secondly, IPFS turns files into DAG. Merkle DAG is where links between objects are cryptographic hashes of the target. Merkle trees ensure that data blocks exchanged on peer-to-peer networks are correct. And finally, IPFS uses something called a distributed hash table or DHT to support the discovery of content and peers. A hash table is a database of keys to values. So when you hear someone say something like get it from the network, what they're actually saying is query the distributed hash table. The second fulfilled requirement is confidentiality. Our system has a private IPFS network. Nodes in the network do not respond to communications from nodes outside the network. The private network allows IPFS to only communicate to peers who have a shared secret key. That's why the generated swarm key allows peers to join the GOT network. Swarm key will be referenced by all the nodes in the private network. In the private network, we have two types of nodes, a bootstrap and a client. The IPFS bootstrap is the way with which IPFS daemon learns about all the peers on the network. And finally, all Git objects are encrypted using symmetric key encryption. Here comes the third and final step to ensure data replication, using IPFS cluster. It works as a sidecar to IPFS peers that can be deployed on top of IPFS for automated replication and better management. Cluster peers in the private network use the cluster secret to manage peer access to the cluster. By adding a file to the cluster, with the file hash, we can ensure that data is pinned among all cluster nodes. Data is first replicated among the peers with the highest available storage, and other configurations can be set, such as the minimum and the maximum replication factors. Now let's start building together the first component in the system architecture. We have the IPFS peer and the IPFS cluster. IPFS cluster is used as a means of automatically replicating and pinning content throughout the IPFS network of nodes. It needs to be installed on all the IPFS peers that make the cluster. Now I'll pass you over to my colleague Faisal.
So we now talk about the blockchain subsystem. We are using a permissioned blockchain network called Hyperledger. Hyperledger is under continuous development, and its maintenance provides main design alternatives for custom networks. This in turn provides flexibility for future work. Moreover, it provides a convenient way of storing data in not only secure, decentralized ledger, but also in a ledger that is mutable and supports future queries. Hyperledger Fabric implements a membership and service provider that can help you authenticate users in the system and manage the different identities. Moreover, it help make protocols more intact through its smart contracts. And actually, one very great feature here is that you can write the contract in the Golang, and it is better to go for Go since it is a growing language in this field. Now we have managed to solve some challenges through our system. First, the way we store data in our decentralized storage is through a key value ledger, but since we have very complex structures, such as repositories and access control structures, so in order to use the ledger, we have divided down the data and the down mapping between the two different forms in an optimized way. Since many users may be cooperating on the same repository, we had to make sure that mistakes, whether intentional or not, will not affect each other. So we have implemented a validation of transactions to ensure that new data is valid and consistent. In a system such as ours, timestamp is important. For example, you may secure your intellectual property from theft by having people witnessing that they saw your data before in a decentralized system. Also, you maybe it is a deadline that you wanted to ensure that you have actually satisfied, or maybe simply you want to avoid unintentional mistake in your work. In all our cases, in our system, we ensure that the user is assigning accurate timestamp to their histories. How do we do so? Simply, users would normally first file the local timestamp into the commits, and then we have to make sure that they are filing the timestamp in a progressing way. And also we have to make sure that they are filing timestamp that is recent, like within, for example, two days window. Moving to access control, first we manage users in the following manner. Once a user has been granted an access to our system, we request that they choose a username and the public key. The public key can be used then as a way to authenticate their future messages. Yet we also give users the freedom to change their existing user profiles by changing, for example, the username or requesting to add a new public key. First, you need to register yourself as a user in order to have access to the system, including creating or managing repositories. Repositories data are always kept confidential through encryption. In fact, each repository gets a symmetric encryption key on creation that at first only the owner knows about. Moreover, that encryption key is shared or changed in a way that permits having a configurable set of collaborators. We can here see how the blockchain part is being added to our system architecture. So moving on to talk about the good client. Good client is simply what wraps the different components in our system and provides the necessary integration between them. It is a Node.js package that can be used to initialize and manage a good project. Therefore, it is responsible of sending transactions to Hyperledger and data files to IPFS. The good client also uses Git in order to keep track of the different versions of the project and then record the project differences in an optimized way. It is also responsible about implementing encryption and signature in data when needed to ensure security and privacy. Through the command line interface, a user would have access to the following features. Doing things like repository management of adding and cloning and pushing updates, or doing things like repository access, like for example, granting access to a user or revoking it, and doing things like related to internet connection, network connection information. So we now can add also the good client to our architecture, and we can see how it needs the local. It also using the features of local get, and also it communicates with the blockchain and Hyperledger. And to walk you through the process, let's say, for example, that there is a collaborator, and then this collaborator wants to do a change. So he first can look the changes through the exported Git features, and once they do so, they can add the object files containing differences caused by the change to IPFS, and once they get the receipt from IPFS, they can provide the receipt along with other logging information to the blockchain to construct a valid transaction. Once a transaction has been accepted, other users would then query the repo, query the ledger about the repo, and then get the necessary information to construct a repository or to pull changes to for a repository. And once they do get this information, they contact IPFS and they get the needed files, and then they get back again to the blockchain to make sure that they got the correct files. Once this happens, they can now continue with working in the repository. So this is the overall architecture, and I would be happy to answer your questions about it in the end of the presentation. Now Hassan will be talking about the cloud deployment.
So moving on to our cloud deployment of Git of Truth, it was divided into two main aspects. One is the IPFS deployment, and the second is Fabric deployment. So our aim was to automate the process as much as possible, starting from using Vagrant, which is a tool used to configure and manage virtual machines. We used it to deploy the virtual machines on the cloud, and then we created some scripts in order to automate the process of setting up a storage node on the cloud and installing IPFS and IPFS cluster on it. And finally, we set up a virtual network in order to allow for secure communication between the virtual machines. It also worthy to note that our structure could be replicated on any cloud provider, and the cloud provider that we used is Azure. Moving on to Fabric deployment, we also used Azure, but the structure can be also replicated. We have a container-based setup for the Fabric network, where each one of the components of the network runs inside a Docker container. As you can see from the diagram, we have the orders, the peers, and CouchDB, each running inside the Docker container, which allows for faster and more efficient performance and better portability and testability, and limits communication with unnecessary resources. and all of the Docker containers are hosted inside a single virtual machine, which is easier to manage in a development environment, but is not practical for a production environment.
Now let's move on to our demo, and it will be divided into two main parts. The first will be a demo of our website, and the second will be a walkthrough of the main features of Git of Truth through a sample use case scenario.
So let me begin the demo with introducing the main channel from which our potential users will get acquainted with the system and install the Git client package. So this is the Git website. And as you can see, we have here installation and documentation. And these are all the requirements fulfilled by Git, and they are our value proposition. And we have also login and register page in order to register our clients. So let me begin with our first use case scenario, and the aim from this scenario is to introduce main features of the Git of Truth. Let me start with introducing the user's levels of access. We have first the owner, who is the creator of the repo and has the highest level of access. We also have the collaborator, who can pull, push, or share his or her access with other users. We also have read or write, and those users can only push or pull. And we also have revoked users, and those are the users who had previously access but no longer have any kind of access. And finally, the default is no access. Introducing our participants, we have two main participants, Alice, who is an owner, and Bob, who is a collaborator. And our environment will be two computers, a personal computer and CSE Labs computers. So the first step in our use case scenario is to initialize Git repos using the Git init command, and then we will create new Git users in order to generate key pairs and add the public keys of the users to the ledger through the following command, Git client user create. And we will also add the user information to Git configuration using Git config command. So as I said, the first step would be to initialize the Git repo and then create the user Alice. Okay. So as you can see here, the user has been created successfully, and we updated the configuration of Git. So after creating the user Alice adds a new file to the repo and commits the changes locally through git add and git commit, and then adds the repo to Git through Git client add repo. And finally, she wants to authorize Bob as a read or write user through Git client authorize command. So as I said, the second step would be Alice doing some changes locally and committing them, and then adding the repo to Git through Git client add repo command. After that, she authorizes Bob to have read or write access, and we can see it has been successful, and she queries user access in order to make sure that the access has been added. On the other hand, Bob clones the Alice's repo, and after that he adds some changes of his own through git add and git commit, and then pushes them to the ledger through Git client push command. And finally, he tries to authorize Tom as a read or write user. However, this should fail since Bob is a read or write user and he doesn't have such privileges. So moving on to user Bob, the first thing user Bob does is doing the command Git client clone in order to clone the repo added by Alice. And then after that, we can see that it has been successful since the file that Alice has added is there, testalice.txt. And then he does some changes of his own through git add and git commit, and then pushes them to the ledger through Git client push. And as you can see, this was successful. After that, he tries to authorize a new user, Tom, and as you can see, this wasn't successful since he doesn't have the privileges to do such task. And finally, our last part for the use case scenario will be Alice trying to pull Bob's changes, and after that, she decides to revoke access from Bob. And now we're back to Alice, the owner of the repo, who does a got client pull command in order to get the changes that Bob has added to the ledger. And as we can see, the changes of Bob are there since we have test bob.txt file. And then she revokes access from Bob. And as you can see, it has been successful since from this command, the query uses access, we can see that access has been revoked. So now let's head back to user Bob, who does a got client pull command in order to get the changes of Alice. But since Alice revoked his access, we can see that the command wasn't successful since he doesn't have privileges.
And now Merola is going to introduce our empowerment outcomes and the business model of Git of Truth.
Okay, so now our empowerment outcomes. So our main empowerment outcome is the open source commercial software product. So up to this point, we have achieved the following listed features, which fully fulfill our system requirements. So in Git of Truth, members of organizations that are subscribed to Git of Truth can do the following. So firstly, they can register to Git of Truth by their keys. They can share their Git repositories through the common channel. They can clone the repo locally on their machines. And of course, they can add or remove Git branches, and they can push and pull changes to the repos. And finally, they can add or revoke collaborators. We also achieved tamper-proof and fully distributed repositories. We added that the replication techniques can be customized according to the organization's needs. We also deployed Git of Truth on the cloud, and we have an initial version of a user-friendly website. Our second outcome is an early draft of the research paper in order to document our whole process. Now the business model. So we developed our business model based on the first use case mentioned earlier. And in this use case, our targeted customers were the software developers, either in companies or in academia. However, this is just an initial plan. So for later, we will allow for the other use cases, and we will allow for a user-friendly interface for everybody to use. So for our customers, we offer the following value propositions. So we offer data integrity, accountability, cost saving, reliability, confidentiality, and data replication. So the communication with the customers will take place by the Git of Truth website, and of course the Got client package that can be used by the customers. We will also build a very good relationships with our customers through the personal assistance and the platform support. Our key partners are Git, IPFS, Hyperledger Fabric, and Azure Cloud. So the key activities that we will make to make profit, we will have the system development platform operations, and we have the customer acquisition. And to make the business model, our key resources are the storage network and the infrastructure technology talent. So Git of Truth comes at a cost, and our cost structure is divided into system development cost, platform support and maintenance cost, cloud infrastructure cost, marketing and customer acquisition cost. So in order to make up for that cost, we have our revenue streams. And our revenue streams are divided as follows. So we have two plans. Plan A, a user who will have fully deployed Git of Truth using our storage resources. And in this case, the customer will be charged per remote repo. So it's a pay-as-you-go model. He will also be charged for the system support fees. Plan B, a user will get a version that will be hosted on their own cloud. And in this case, they will only be charged for the system support fees. So we tested, failed, adjusted, and we're convinced that the market potential for this model is enormous. Okay, so at this point, we used to present a timeline, but since it's our last Thesis 2 presentation, we will be presenting the future work and enhancements to Git of Truth. So the ordering service on the blockchain part can be improved by introducing the Byzantine fault tolerance. Also, we can enhance the time management system by imposing a system that is based on a third-party integration of time servers, such as the network time protocol. We can also have a distributed approach relying on the virtual global clock algorithms for distributed systems. We can add timestamp during the block header creation. Also, we can enhance the management of multiple blockchain networks concurrently. We can add the management of multiple IPFS networks concurrently. We can deploy the Hyperledger Fabric consortium on Azure Kubernetes service, and we can have a full integration of the web UI. So now, our final Thesis 2 presentation has come to an end. So I would like to thank our supervisors who were very helpful and supportive all the way in our thesis journey. So I would like to thank Dr. Sherif El-Kassas and Dr. Karim Sobh. And I would like to thank all the audience for listening to our presentation. Thank you, everybody. And now it's time for questions.